The sine and cosine functions. These two functions are easy enough to graph, but what about if we start applying a bunch of weird transformations to them? How does that affect their graphs? That's what we'll be looking at in today's Wrath of Math lesson. We'll go over the transformations we can apply to sine and cosine and why they affect the graphs the way they do. We'll go over a couple good examples of graphing these transformations, but my primary focus for this lesson is getting you to understand those transformations. In the next lesson, we'll work through a slew of gnarly examples of graphing transformations of these functions, so go check that out after this lesson to really sharpen your skills. Just a couple quick things we're going to want to remember to help us graph transformations of sine and cosine. We want to understand these functions and their graphs as much as possible. If we understand them, then we don't have to memorize so much. Some of you might know that sine of 0 is equal to 0. We don't want to just memorize this because then we might screw things up. Let's quickly take the time to understand it. And I'm assuming you're already fairly comfortable with sine and cosine and their definitions. So what is sine of x? Well, we've got this right triangle with an angle x. So sine of x is the ratio of the opposite side, the side opposite the angle, to the hypotenuse, O over h. Now what if we decrease this angle x? Well then our right triangle might look something like this blue right triangle I'm drawing on top of the green one. And we can see the length of this opposite side is shrinking as we decrease the angle. Then, if we decrease this angle all the way to 0, well, the opposite side is kind of non-existent. It has a measure of 0. So, of course, sine of 0 is equal to 0. And then, of course, some of you may know that cosine of 0 is equal to 1. And we can reason through this the same way. We've got this right triangle with an angle measure x. Cosine of x is the ratio of the side adjacent to the angle, this side A, to the hypotenuse. So it's A over h. Now as we decrease this angle, the length of the hypotenuse is actually getting closer to the length of the adjacent side. If we decrease the angle all the way to 0, the hypotenuse and adjacent side sort of merge into one. They have the exact same length. So of course, cosine of 0 is going to be 1. One other quick thing I want to make sure we all understand before we get into looking at transformations. Well, this is really looking at transformations already. Let's take a look at our unit circle just so we can understand a particular type of transformation. So this is our unit circle, a circle with radius 1. We can say the measure of this angle is x. This, of course, is a right triangle. So the sine of the angle x is the height of the opposite side, which is the y-coordinate of this point. Of course, technically, it's the length of this side divided by the length of the hypotenuse, but this is a unit circle. So this hypotenuse, which is a radius of the unit circle, has a length of 1. So dividing by that length doesn't change anything. But what if we look at sine of negative x, the same angle measure, just negative? Negative angles open up into the third quadrant, so negative x looks something like that. Sorry if you can hear that loud train in the background. Now, just as before, sine of negative x is the y-coordinate of this point. Clearly, the y-coordinate of that point is negative. So the y-coordinate of this point is negative, but the point is also just as far away from the x-axis as was this point. So the big takeaway is that sine of negative x is equal to negative sine of x. You might recognize this as fitting the definition of what's called an odd function. If we ever have a sine function like this, where x is getting multiplied by negative 1, we're going to want to rewrite it like this, taking that negative out in front of the sine function. That's going to make things a bit easier to understand. We cannot do the same thing with the cosine function, however. What is cosine of this positive x angle? Well, it's the x-coordinate of this point. It's just the length of this adjacent side. Again, dividing by the hypotenuse with length 1 doesn't do anything. Then we can see that cosine of the negative x angle, that's the x-coordinate of this point, which is exactly the same as the x-coordinate of that point. So the takeaway there is that cosine of negative x is actually just equal to cosine of positive x. So again, if we've got a cosine function like this, with -1 being multiplied by x, we will want to remember this property and rewrite it like this, and that's going to be easier to work with. Then the one last thing we want to make sure we remember before we start really digging into transformations, we can see just looking at a circle, once we do a full rotation around the circle, the values start repeating. We hit the same points again. Now we'll be talking about angles in terms of radians, so how many radians are there in a circle? You might recall there are 2 pi radians in a circle. If you don't know why that is, think about or look up what a radian is, and then it becomes pretty clear why there are 2 pi radians in a circle. It has to do with the circumference equaling 2 pi times the radius. But anyways, since there are 2 pi radians in a circle, both sine and cosine have what we call a period of 2 pi. Their values start repeating after 2 pi units. Alright, I think we are thoroughly prepared. Let's start looking at some transformations, and we'll see why these transformations affect the graphs of these sine and cosine functions the way that they do. And for the most part, everything we say about these transformations is true about both sine and cosine. We just have to remember that sine of 0 is 0 and cosine of 0 is 1. And we've got to remember these two properties. Sine of negative x is negative sine of positive x, and cosine of negative x is cosine of positive x. Alright, back to our graph. We should all be fairly familiar and comfortable with graphing these functions without any transformations. Sine of x, of course, looks something like this. What we'll focus on a lot in graphing these transformations are what we'll call key points. There are 5 key points in a single period of the sine and cosine functions, where it starts, its peak, where it intersects what we'll call the midline, its lowest point or trough, and then where the period ends. If we can identify 5 key points of a single period of a sine or cosine function, then we can graph it. In the case of our basic sine function, this highest point has a y-coordinate of 1. The lowest point has a y-coordinate of -1. We know that the period of the sine and cosine functions is 2 pi. So here, where the period ends, has an x-coordinate of 2 pi. It's really helpful to notice that each of these key points is a fourth of the way along the period. 0/4 at the first key point, and then 1, 2, 3, 4. Now this is very helpful for labeling our graph, because what's a fourth of our period? Well, that's 2 pi over 4, which reduces 2 pi over 2. So once we've identified our first key point, which in this case is 0, 0, the next key point is pi over 2 units away on the x-axis. In this case, of course, those units are radians. So this peak here has an x-coordinate of pi over 2. Then traveling another fourth of the period along, another pi over 2 radians forward on the x-axis, this next key point, well, that's going to be pi over 2 away from this. That's going to be pi, because pi over 2 plus pi over 2 is pi. And then what's the x-coordinate of this trough? Well, that's another pi over 2 forward on the x-axis. Pi plus pi over 2 is 3 pi over 2. So that's the x-coordinate of this point here, and remember we know its y-coordinate is -1. And there we go, we could continue labeling this graph if we wanted. This next key point would be another pi over 2 radians forward on the x-axis, and so on. If you master these basics, graphing the transformations becomes pretty easy. Let's apply a simple transformation to this sine function. Suppose we add 1 to the end. How does that affect the function? Well, this value that previously had a y-coordinate of 1 will now jump up to 2. Similarly, this point, which had a y value of 0, is going to jump up to 1. And that's going to be the case for every point on this graph. They all jump up 1 unit. So adding 1 to the end of our sine function has the effect of moving its graph up 1 unit. Now, what we're calling the midline of the sine function was at y equals 0. Now that we're adding 1 to the end, the midline is at y equals 1. That, of course, is this line here. The importance of the midline is that the sine and the cosine function, they intersect the midline every half period. So here at the start of the period, they intersect the midline, and I know it's not drawn perfectly. And then here, halfway through the period, intersects the midline again, and then another halfway through the period, which completes this first period, intersects the midline again. The midline is also useful because the distance from the midline to the peaks of the sine function, which are the same as the distance from the midline to the troughs, this is called the amplitude of the function. And we'll talk more about amplitude and transformations of it in a little bit. Of course, if instead of adding 1 to the end, we had subtracted 1, then our midline would be y equals -1, and the function would be shifted down 1 from the original sine function. So here is our original sine function. Subtracting 1 has the effect of shifting it down a unit. And maybe move it down just a little bit more so the graph lines up nicely. So those are the effects, pretty straightforward, of what's called a vertical shift. This is the more general form of the sine function that we're going to get comfortable graphing, this form that allows all these sorts of fun transformations. Looks kind of gross. This d on the end, that is our vertical shift. And you can see if we just plug an x-coordinate into this function for an example, say we plug in 0, sine of 0 minus 1 is equal to 0 minus 1, which is equal to -1. We can see how that sine of 0 value, which is equal to 0, has been shifted down 1 unit. And the same thing happens to the rest of the points on the graph. They all go down 1 unit. Alright, next we'll talk about this c. That's called a phase shift. Let's go ahead and do some more graphing. Let's say we've got this transformation, y equals sine of x minus pi. So now, instead of adding or subtracting a number after the sine function, we're adding or subtracting a number from x directly inside the sine function. A common mistake is to think that since this is a negative value, minus pi, it will shift our sine function left pi units. But that's not what happens, and if you think just a little more carefully about it, I think you'll see why. We, of course, like to start graphing our sine functions at sine of 0. But with this transformation, sine of 0 doesn't occur at x equals 0. If we want to see where sine of 0 is, we just have to set the inside of the sine function to 0. So we have x minus pi equals 0, solve for x, and we see that x equals pi. This means that when x equals pi, the stuff inside our sine function will be 0. Pi minus pi is 0. And so this actually has the effect of moving the sine function forward pi units. So whereas the first key point used to be at x equals 0, now it's at x equals 0 plus this phase shift of pi, which is of course pi. Similarly, whereas the end of the period used to be at 2 pi, now it's at 2 pi plus the phase shift of pi, which is 3 pi. The way I like to think about this is since we're taking a number away from x by subtracting, we need greater x values to get the same y values we were previously getting, which is why the graph of the function moves forward. Now, what if we add pi instead of subtracting pi? Well then, we could set the inside of the sine function equal to 0 again, and find that when x is equal to -pi, that's when the inside is equal to 0. In other words, the original sine function gets moved back pi units. Because since we're adding something to x, we need smaller x values to get the same y values we were getting before. And that's why the function moves left in the negative direction. And again, that's called a phase shift. To find the phase shift, we just set the inside of the sine function equal to 0. Then by solving for x, we find the x-coordinate of our first key point, which is where we start drawing the function. But it's a pretty simple transformation. It doesn't stretch the function in any way, it just moves it a little bit to the left or right. And again, looking back at that general sort of function we're building up to, this was that c value. Next, let's talk about this b. It's going to affect the period of the function, and it's probably the most complicated type of transformation. And we're dealing with a cosine function this time. Again, remember, pretty much all of this stuff is true for sine functions and cosine functions. You've just got to understand those differences we went over in the beginning. So here, because I think it will be helpful, I included also a phase shift transformation in this example. What's going to be helpful is if you write your sine and cosine functions so that x has a coefficient of 1. It's not necessary, but you might find you prefer doing it that way. Let me show you why. So in this case, since x has a coefficient of 3, we'll factor out a 3 from both of these terms, which gives us cosine of, we factor out that 3, so then we're left in the parentheses with x minus pi. What's nice about this form is that it lets you immediately pick out the phase shift. We see here we've got x minus pi, so that's a phase shift of pi, positive pi, radians forward, moving the function right pi radians. You'd be able to figure that out by doing what we went over earlier, set the inside of this equal to 0, and then solve for x. You would have 3x equals 3 pi, divide both sides by 3, and x equals pi. So positive pi is our phase shift. But again, it's really easy to see when it's written like this at a glance. Since you have x minus pi, it's a phase shift of positive pi, which moves the function forward pi radians. Alright, enough about that. Let's talk about the new transformation we're dealing with. So like I already said, multiplying x by some number, in particular a number that isn't equal to 1, is going to change the period of the function. And if you think about this, that should make sense, because how do we complete a period in a sine or cosine function? Well, we have to go from cosine of 0 to cosine of 2 pi. Of course, you could start at whatever value you want. You could go from cosine of 3 to cosine of 3 plus 2 pi. The point is, for a whole period to take place, the inside of the cosine or sine function needs to increase by 2 pi, or decrease by 2 pi. That part doesn't really matter. But when the inside changes by 2 pi, that is a whole period. When all we have inside our function is x, x clearly has to change by 2 pi for a whole period to take place. But when x is getting multiplied by something, that is no longer true. So let's see this. We already identified that our phase shift is positive pi. So y is equal to cosine of 0 at x equals pi. The end of that period will be at y equals cosine of 2 pi. How much does x have to change to get the inside of this function to 2 pi? Well, let's set the inside equal to 2 pi and find out. So we have 3x minus 3 pi equals 2 pi. We'll see as well that this phase shift doesn't affect the length of the period at all, but we're including it in the calculation so we can see that in action. To solve this for x, we'll add 3 pi to both sides, so 3x is equal to 5 pi, and then we'll divide by 3. So x is equal to 5/3 pi, which you could also write as 2/3 pi plus pi. Writing it like this lets us see that x had to change by 2 pi over 3 from where it started at cosine of 0 in order to get us to cosine of 2 pi. In other words, the total change in x to complete the period, to go from cosine of 0 to cosine of 2 pi, that period length we'll call p, is the x value at the end of the period, 2/3 pi plus pi, minus the x value at the beginning of the period, which was just pi. Here we can see how the phase shifts cancel out, and we're just left with 2 pi over 3. And this would work the same way with the sine function. So what we see is that sine and cosine, they normally have a period of 2 pi. But when we multiply x by some number that's not equal to 1, in this case 3, we have made it so x needs to change 1/3 as much in order to complete a whole period. So the period length is the original period, 2 pi, divided by that factor of x, which in this case is 3. Since x has to change less to complete a whole period, this transformation has the effect of sort of squishing the function inwards. So our period, again, we figured out, is 2 pi over 3. So with sine and cosine functions, when x has a coefficient that isn't equal to 1, if it's negative, you first want to apply the property we talked about at the beginning of the lesson to make sure that x has a positive coefficient. So if this were, for example, cosine of negative 3x plus 3 pi, first I'd factor out a negative 1 inside, and that would give us cosine of negative 3x minus 3 pi. And then I know that cosine is an even function, so cosine of some negative input is equal to cosine of that same input if it were positive. And so in this case, we're able to drop that negative. If this were a sine function, we'd have to pull the negative out in front. Once you've done that, to see what your new period is, you just divide 2 pi by that coefficient, in this case 3. So our period is 2 pi over 3. Let's do a graph. And of course, we'll also want to remember that our phase shift, which I'll just call c, our phase shift is positive pi. I'm actually going to move this y-axis over to the left a little bit because for this example, we'll want some more room on the x-axis. And I'm actually going to move the x-axis up a little bit so everything fits on the screen. The high point of the cosine function is 1, the low point is negative 1, and then our phase shift is pi, so our first key point in our first period, that's going to start at x equals pi. And we know cosine of 0 is 1, so at our phase shift pi, we've got a y value of positive 1. Then, since our period is 2 pi over 3, the next key point is a fourth of that along the x-axis. What is a fourth of 2 pi over 3? Well, that's 2 pi over 3 times 1/4, which is equal to 2 pi over 12, which we can reduce to pi over 6. Now here's something I just noticed that you should definitely pay attention to while making these graphs. I thought I had drawn this first x-coordinate far enough along on the x-axis, but I realized I probably didn't, because our period is less than our phase shift, which means from here at x equals 0 to the phase shift, there should be more than one full period of the function in that space. That looks like it would be pretty crammed. So to try to keep everything to scale, let's move this first x-coordinate a little bit further along on the x-axis. So we'll erase that and put it further out, let's say right here. That's pi. And our first point is at pi positive 1. And now it seems like it would not be so crammed for a whole period of the cosine function to fit in that space. Alright, now just a minute ago we figured out that a fourth of our period is pi over 6. So the next key point is pi over 6 further along on the x-axis. So what is pi plus pi over 6? Well, that would be 7 pi over 6. So that is the x-coordinate of our next key point. And let's say that's about there. This is where the cosine function intersects the midline, which in this case is y equals 0. Then the next key point will be another pi over 6 units forward. Pi over 6 plus 7 over 6, that is 8 pi over 6. So let's say that's right about there on the x-axis. See if I can shrink that a little bit. And that key point is going to be down at negative 1. And then I think you can see how this is going. The next key point is 9 pi over 6. We'll actually zoom in to write that one. 9 pi over 6. And that's going to be here at y equals 0, intersecting the midline. And then it goes back at 10 pi over 6. That's the next key point. Another pi over 6 radians forward on the axis. 10 pi over 6. And that's where it gets back to the start of the cycle or period at y equals 1. And then, of course, you might want to reduce these fractions. Let's zoom in and do that. 8 over 6 pi, that can be reduced to 4 over 3 pi. Then 9 and 6, they both have common factors of 3. That's 3 pi over 2, that gets reduced to. And then 10 pi over 6, 10 and 6 have a common factor of 2. We can reduce that to 5 pi over 3. So there we go, we've got our reduced x-coordinates. Now we can go ahead and draw this one period of the cosine function. And of course, if you wanted to draw more periods, you could try to rough hand sketch it, or you could keep adding a fourth of the period to these x-coordinates to locate your next key points, and you could subtract pi over 6 from this x-coordinate to get this key point, and then subtract another pi over 6 to get the x-coordinate of that key point, and so on. But certainly, if you can draw one full period of the transformed function, you're in pretty good shape. It's pretty easy going after that. So again, in the sine and cosine functions, multiplying x by some number not equal to 1 affects the period. If we multiply it by some number greater than 1, the period is decreased because x needs to change less in order for the inside of the function to change by 2 pi. If we had multiplied x by something less than 1, like say 1/3, then x would need to change more to cause a total change of 2 pi in this function, and so the period would be increased by a factor of 3. In that case, the period would be 2 pi over 1/3, which is equal to 6 pi. And again, I think that's the trickiest type of transformation. Going back up to the more general form of the function we were looking at, what we were just looking at was a number in the position of b. And of course, we were looking at it in the case of a cosine function. And this is not supposed to be d squared, by the way. That 2 is just in a bit of a bad spot. Let me go ahead and move that over there. Alright everyone, I hope you're still with me. We are moving on to the final type of transformation that we're talking about in this lesson. And this one is pretty straightforward, so let's go ahead and get into the graph. I think we used sine for 2 of our examples so far, so let's go ahead and change this sine to cosine so that we can use cosine again as well. So here, pretty simple, we're just multiplying the cosine function, or sine function, by a number. Doing this has the effect of stretching or compressing the function vertically. It's kind of like changing the period, except changing the period stretch and compresses the function horizontally, whereas this transformation stretches and compresses it vertically. Because now, when we plug some number into our function, say 0, cosine of 0 is equal to 1, but now that's getting multiplied by 2. So I'm going to go ahead and graph the normal cosine function, and then we'll look at this transformed version on top of it. So here is one period of our normal cosine function. When we multiply it by 2, pretty simple what happens. Where it was equal to 1, it will now be equal to 2. It gets doubled. Where it was equal to -1, it's now equal to -2. And the same thing is true for all of the points in between those peaks and troughs. Their y-coordinates are multiplied by 2. And this is pretty easy to graph. So cosine of 0, it's going to start at 2. Then, since we don't have any vertical shift, it's going to intersect the midline at y equals 0, just as usual. And then its lowest point is all the way down here at -2. Then it goes all the way back up to the midline, and then back up to its peak to finish the period. Then I'm going to zoom out a little bit. You don't usually see this. Zoom out a little bit to hopefully help me graph this a little better. Looks something like that. So it's just a vertical stretch. More technically, this is a change in the amplitude. We mentioned earlier how the amplitude of a sine and cosine function is the distance from the midline to the highest point, which is the same as the distance from the midline to the lowest point. Typically, the amplitude of these functions is 1, but when we put some factor in front of the function, that factor becomes the new amplitude. So in this case, we can see our amplitude is 2. The distance from the peak to the midline is 2. If instead we had multiplied the function by some number less than 1, say 1/2, then the cosine function would be compressed vertically, so its amplitude, its highest point and its lowest point, would be 1/2 from the midline. And if I graph that in this pink, that would look something like this. And that's how a change in the amplitude works. Again, looking back at our general functions, that's this number a. So you might be able to have some luck graphing transformations of sine and cosine now. But again, the primary focus of this lesson was to get you to start understanding these transformations. In the next video, we'll really dig into some examples to get a better grasp of how to graph these transformations. Then, one last thing before we go, let's jump over to Desmos and see some of this in more animated action. So here is our normal sine function. We see it's got its first peak at pi over 2, intersects the midline at pi, and then 3 pi over 2 is the low point, and then it finishes the first period at 2 pi. We can see as we change the value d, the sine function moves up and down. This is that vertical shift that we talked about at the beginning. As we change c, the phase shift, the function moves left and right. And we can see, looking at this value c, as the value of c increases, the function moves left. As the value of c decreases, the function moves right. Which again can seem kind of counterintuitive at first, but by setting the inside of the functions equal to 0 and then solving for x, we can get a clear idea of what the phase shift is. And then b, the number that gets multiplied by x, that changes the period of the function. That's perhaps the most fun one. So as b changes, we see the function compressing and expanding sort of like a spring as the period decreases and increases. The bigger b is, the smaller the period is. And the smaller b is, the closer it is to 0, the longer the period is. We can see that if I grab a hold of b here. As we get close to 0, less than 1, we see that period is getting really stretched out. And then it gets shrunk, it gets squeezed together as we increase b. Because x needs to change less when it's getting multiplied by a number greater than 1 in order for a full period to take place. And then lastly, changing a, the factor in front of the function, this changes the amplitude of the function. If a is less than 1, so it's getting kind of close to 0, the amplitude shrinks. And if it's greater than 1, then the function is stretched out. Something we didn't see in this lesson, which we'll see more of in the next lesson, if a is negative, then the values of the function are reflected across the y-axis. So we're used to the sine function going up from 0 and then going back down, but when a is negative, the sine function goes down from 0 and then back up. And then with cosine, we're used to cosine starting at its peak and then going down. But if a is negative, then cosine starts at its lowest point and then goes back up. So hopefully that seems pretty reasonable. If we multiply a function by a negative number, its positive values become negative, and its negative values become positive. And that should just about do it. So I hope this video helped you understand the transformations of sine and cosine functions and how they change the graphs of the functions. I hope you'll check out the next lesson where we dig more into graphing examples of these transformations. Let me know in the comments if you have any questions, need anything clarified, or have any other video requests. Thank you very much for watching. I'll see you next time, and be sure to subscribe for the swankiest math lessons on the internet. And a big thanks to Valo, who, upon my request, kindly gave me permission to use his music in my math lessons. Link to his music in the description.